Hello and welcome back. Today I'll be delving into the mathematics behind musical tuning systems. Firstly, we'll start with the basics of a scale. This is the standard 12-tone scale used throughout the world. Today we'll be using the tuning standard A is equal to 440 Hz. For those who don't know, in Western music, an octave consists of 12 steps known as semitones, or halftones, depending on if you're British or American. In the English-speaking world, these notes are known as A, B, C, D, E, F, G, and also these letters with sharp signs and flat signs. When we go up a step in a musical scale, we change the letter. We use the next letter in the musical alphabet until we loop back to the beginning. In this case, we're starting with A, and then we loop towards A again. When we loop back towards A, we have what is called an octave, and physically this corresponds to twice the frequency. Today, I'll be investigating different methods of assigning frequencies to the other notes in between so that we have a nice coherent scale. Let's start with the very first, Pythagorean tuning. This was famously used by Pythagoras himself, although it was known to multiple cultures before. This system is based off two overtones in the harmonic series, the octave and the compound perfect fifth. That is a note that is a fifth further than an octave. Using these intervals gives us a frequency ratio of 3/2. We can now use this frequency ratio to generate all the other frequency values. Firstly, we'll start with A. We'll go a fifth up, which is E, and to do that, we'll multiply the frequency by 3/2 for 660. Then we'll multiply by 3/2 again. This takes us to B, the octave above, at 990 Hz. Here we'll divide by 2 to get 495 Hz, just to take it back down to the original octave. From here, we can multiply again by 3/2 to get F sharp at 742.5 Hz. Note here that I am keeping all of these frequency values to one decimal place. From there, we can multiply by 3/2 again to get C sharp, the octave up, as 1113.8 Hz, and then we can divide that again by 2 to get C sharp as 556.9 Hz. Using this method, we can fill out the entire table. However, now that we've filled in D, you'll notice that if we multiply by 3/2 again, we have an issue. When we multiply from D to get A, the octave up, we find that we have a calculated frequency of 892. In music terms, this is almost a quarter tone out from where A should be, and this difference is known as the Pythagorean comma. This comma here is a major reason why Pythagorean tuning was later supplanted with more sophisticated forms of tuning systems. Another issue that means it is not used in modern day music is that the third, which in modern day music is considered consonant, is out of tune in the Pythagorean system. There is, however, one small use case remaining for the Pythagorean system. Players of scale-free instruments, such as violin family instruments or voice, still use the Pythagorean system for runs based on scales, as these make scales sound in tune. Scale-free instruments are simply instruments where there is no fixed pitch, and you can tune any note precisely as you want it. Now we'll move on to just intonation, the intonation system which quite quickly replaced Pythagorean tuning. The variant of just intonation I present here is known as 5-limit just intonation. This is because, of all the fractions that are used, the largest prime number to appear either as a factor or on its own is 5. Compare this to Pythagorean tuning, which is in fact simply a form of just intonation where the largest prime number is 3. In just intonation, the ratio between the tonic, that is the first note A, and a perfect fifth is still 3/2. However, the ratio between the tonic and the perfect fourth is 4/3, and the ratio between the tonic and the major third is 5/4. Using these three ratios, we can, for example, calculate F sharp or G flat. This is equivalent to taking 5/4 multiplied by 4/3, and this gives 5/3. Using this method, we can now fill in the entire table. Notice, however, that using this to calculate the augmented fourth and diminished fifth actually give different frequencies. The augmented fourth is in blue, 618.8, and the diminished fifth is in red, 625.8. These are only 7 Hz apart. However, at frequencies around 600 Hz, human ears can detect frequency changes on the order of about 1 Hz, and therefore this change is fairly substantial. In the modern day, just intonation is used by the same scale-free instruments above. However, it's more likely to be used for arpeggios, since these make arpeggios sound more in unison. Just intonation is also usually used for tuning pentatonic scales by ear. Pentatonic scales are simply scales with 5 notes in the entire octave, and are heavily utilized in multiple cultures and also in some very famous pieces, such as Dvorak's American Quartet. Now we'll move on to the modern system, equal temperament. This system is much simpler mathematically, although it was very, very hard to calculate initially due to the difficulties in calculating the ratio. Here, in a 12-note scale, we simply have to calculate the 12th root of 2. This number, however, was quite hard to calculate and wasn't calculated until the 1500s. Using this, we can simply multiply by the 12th root of 2 to find every single note. This scale is used by most modern instruments, including modern woodwind, brass, and pitched percussion, including piano. Keyboard instruments were some of the first instruments to adopt equal temperament, as the system suited keyboard instruments very well. Instruments that would normally on their own be using Pythagorean or just intonation will switch to equal temperament to play with instruments such as pianos or fretted string instruments like guitars. If you liked our video, please like and subscribe, and we'll see you next time for some more fun maths problems. Thanks for watching, and goodbye.